Section 3.3 is sort of an extension of Section 3.1, where in Section 3.1 we had systems of linear equations, but they were two equations with two variables, and now here we've got three equations with three variables. There are some things that are going to remain the same, but there are going to be some things that are new here. So one thing that's the same is the types of solutions that you can have. Like the different types of outcomes at the very end after you've done all the solving. You could have one solution, you could have infinitely many, or you could have no solution. So it's the same three overall concepts that we would have had in 3.1. Although what these things actually mean would be a little bit different graphically. So graphically, when you have two equations with two unknowns, that's two lines, right? And that's how we talked about it in 3.1, where if you get the one solution, that's two lines intersecting in a single point. If you get the infinitely many solutions, that's where one line's on top of the other. And if you get no solution, they're parallel, right? But when you have three equations with three variables, then an equation with three variables in it, that's going to have three axes. So like if you were going to graph this, it would have to be three-dimensional. So you'd have your horizontal axis and your vertical axis like you normally do. The third one would basically, like if you're looking at a piece of paper like this, then, so you'd have a horizontal axis like that, right? And a vertical one like this. And then the third axis would like come out and go back into the paper, right? That would be the third dimension that you would add in. So an equation of this form where you'd have an x, y, and a z term in there, so this is in standard form right here, that's not a line, it's a plane. So that's a little bit different. And you're never going to have to make the graphs, but I figured it was actually worth kind of talking about this a little bit because I think for a lot of people, it becomes harder when it's difficult to visualize. And the two lines isn't really that hard, right? Like if you want a mental image of two lines intersecting, that's not too hard to come up with. But, you know, what does three planes intersecting look like, right? Like that's tough. So I figured that's why this stuff needed to kind of go in here, at least a little bit. So to get one solution where your solution is just one point, so you'd have an x-coordinate, y-coordinate, and a z-coordinate, so you get an ordered triple instead of an ordered pair because you got three coordinates now. But with one solution, you can have that where it's three planes that intersect in a single point. And that's actually what in these pictures down here, that's this one. So the one that's on the far right, that's one where the three planes intersect in a point. So it's the point right in the middle, right? So you can kind of see it right there, right? Because you got like the plane that's like up and down, I guess like parallel to the way that the paper is. And you got the one that's supposed to be almost like lying flat. And then you got this one sort of coming like right out, just like its edge would be coming right at you. That's how that's supposed to be drawn. They intersect in just that one point, right? If you pick any two planes, they're going to intersect in a line, but all three only intersect all in that one spot. Infinitely many solutions you can have if the three planes intersect in a line, which would be like this. So it's this one right here. That's the intersect in a line planes. So these three intersect in a line, which you can see, it's like you can see part of it. It's right here. Right? Because that line that's going right through there, all three planes contain it. So that's another option. Or, and our book brings this up, like if you look in our book, this is on the first page of this section, what if all three equations are multiples of each other, then they're all going to be the same plane? That's true, although I don't think that actually comes up in this section anywhere. Like I don't think there are any problems where that's going to happen. And then no solution has a bunch of different looks because you've got three things, and as long as they don't all intersect in the same spot, there's not going to be a solution. So you can have three parallel planes. That's this one in the upper left. Two parallel planes with a third intersecting those two. That's this one in the lower left right here, right? The two that are going up and down are supposed to be parallel. And then that third one's going through both of them, but they never intersect all together. Like you don't have all three. then this thing over here, right, this is just another weird one that would give you no solution, because there's never going to be a place where all three planes intersect, right? Sure, every plane intersects every other plane, but it never happens at the same time. Like, you never get all three together. So there are a lot of ways that you can have no solution. I guess that part's kind of new. And the idea that, when you have the intersection, it's going to look different, like when you actually do get an intersection of some kind, just because there's that extra dimension, right? Because everything's three-dimensional now. Okay, first thing is to determine if an ordered triple is a solution. Well, you would have to check all three equations. Just like before when we had two equations, you had to check them both. Here, since you got three of them, you'd have to check all three. So the first equation, so first, I guess, meaning the one on top, x plus y plus z equals 5. And if we substitute in to see if that ordered triple satisfies it, we'd have -1 plus 2 plus 4. And then we just have to see, is that going to be 5? Well, -1 plus 2 is 1. And 1 plus 4, yeah, that works, right? 1 plus 4 is 5. Then the second equation, all right, we got 2x plus 3y minus z equals 0. And if we sub in, we'll have 2 times -1 plus 3 times 2 minus 4. And we just have to see, well, is that going to be 0? Well, that's -2 plus 6 minus 4. And it looks like we're good, right? Because -2 plus 6, again, well, that's 4. 4 minus 4, yeah, that's 0. All right, 2 down, and so it all hinges on this. If the third equation is satisfied by that point, then the point is a solution, and if the third equation is not satisfied, then it's not. So we've got x minus y plus 5z equals 21. And if we sub in, we're going to have -1 minus 2 plus 5 times 4. Uh-oh, it looks like this is going to be a little too small. This is going to be -3 plus 20. And that is not 21, right? Because that is 17. So it's not 21. This doesn't work. So no, it's not a solution, because in order to be a solution, it would have to be a solution of all three. And we got the first two. We didn't get the third one, so we didn't get all three. All right, well, there's a little bit of this in this section of just checking to see, is this ordered triple going to be a solution to this system of equations? But mostly what you end up doing is trying to solve a system of equations. So how do you do it? It's a little bit different, although there are parts of this that end up being actually the exact same sort of thing we were doing in 3.1. Basically what you try to do is you take your system of three equations and you try to manipulate it a little bit so you get something that's like what we were doing in 3.1. What you do is you pick a couple of different pairs and get rid of the same variable in both, and then that way you're left with two equations and two unknowns, and then you go, 3.1, we know how to do this. So what you do is, and the book writes this out differently than I do. I know they have it where they have like, this is equation 1, 2, and 3, and then you have to make your 4, and then you make your 5, and then there's a lot of extra itemization there, which for me, it feels like that makes it harder. One of the things that I always thought made sense as far as trying to remember how to do math stuff is I always tried to do it by having to remember as little as possible. I figured that's better in a way, just because then you don't have to keep as many things straight. But also, it made me kind of feel like I was more flexible. I don't know if that's real or not, right? That could have just been, like some psychological trick I was playing on myself. But that's always kind of what I gravitate toward. And the way that I think about it, I don't think about like 1, 2, 3, 4, 5, like with all the different equations being labeled. For some people who really like to itemize stuff, that probably helps. I mean, I guess it just depends. But the way that I look at it And plus, if I do it my way, it'll be a little bit of a different look than what's in the book, and I figured that's probably the best thing I can do. So what I would do, where it says pick two equations, it doesn't matter which two. What I would do is, before I even did anything, like if I get a system of three equations and then I got to solve this, the first thing I do is put the pen down, because I want to make sure I look over the whole thing and figure out what variable is going to be the easiest one to get rid of. And the best thing to look for is if there's an additive inverse somewhere. Like let's say, just hypothetically, I'm just going to write stuff down. I have no idea what this is going to work out to be. So I'm just going to make up a bunch of things here. And I don't know, 5x plus 2y plus 4z equals 28, let's say. If I was going to do this, so to eliminate one of the variables, I would pick the first and the third. And the reason for that is because the way that you eliminate one of the variables is by manipulating one or both of the equations, by multiplying both sides of the equation by the same number and then adding them together, where you try to add one of the variables out, right? You try to get additive inverses. What I look for is, are there any additive inverses already? So here, I would just look over the whole thing and eventually I'd go, all right, minus 2y plus 2y. If I add those together, I can get rid of y in that first pair without doing any work. That sounds good, right? So that's what I would do there. Like I would pick those first. So I would go, all right, we got 3x. So I guess this would be my first pair over here. I would pick those. I'd have 3x minus 2y plus z equals 6. And then I'd have 5x plus 2y plus 4z equals 28. And then I would add those together and I'd get 8x. I'd have no y term because those are going to add out, plus 5z equals 34. And then for your second pair, you've got to use the equation that you haven't used yet out of the original three. So I'd have to use the second one, and then you got to get rid of the same variable again. So in my case, I'd be getting rid of y again. And you can pick either the first or third to pair up with the second. You have to manipulate one of them or both of them. In this case, I would pick the first because the y terms already have opposite signs. So what I would do for my second pair is that I would say, well, I need the x plus 4y minus 3z equals negative 2 because I haven't used that yet. But then I'm going to take the top one because the y terms have opposite signs, right? This one's negative. And then I want to get rid of y again. So I would just multiply both sides of the bottom one here by 2. And then that way I'd have a 4y on the top and a negative 4y on the bottom. So what I would do is I would just leave this top one alone. So x plus 4y minus 3z equals negative 2. And then I would multiply both sides of the bottom one by 2. And then, so I've got x plus 4y minus 3z equals negative 2. And then I've got 6x minus 4y plus 2z equals 12. And if I add those together, I'm going to get 7x minus z equals 10. And then notice up here, I've got an equation x and z. Down here, I've got an equation x and z. So basically, what I've done is I've done the first two steps. Then after that, you take those two equations, you'd solve it like you would in section 3.1 because it's two equations with two unknowns. And then once you figure out what x and z are, then you would go back and use one of the original three to solve for y. So you go back here, maybe you pick the first one, you're going to sub in whatever you got for x, whatever you got for z, and solve for y. And then you'll have your full solution, you'll have the full ordered triple. So that is the idea here. And let's see what we got. So with this first example, I think this one actually ends up with a lot of negatives in it. But looking around, there's nothing really that jumps out to me. So just before even doing anything, I'm looking at that and I'm going, I don't see any additive inverses. I don't even see any two terms of any variable that are different signs, because all the x terms are positive, all the y terms are positive, and all the z terms are negative. So I guess it's just whatever you want to get rid of. I did it with z, but you could really pick whatever you wanted. I mean, if you wanted to use x and just say, well, what if I took the first equation, then I took the second one, and I multiplied both sides of the second one by -1, then I've got a 3x and a -3x, and those are going to add out. Yeah, that works. There is no one specific right way to do this. There are a ton, right? I mean, like, you could get rid of x first, you could get rid of y first, you could get rid of z first, and if you're going to get rid of x first, there are 3 different pairs that you could pick, and you have to pick 2 of those. Right? I mean, there are all kinds of options for how you can get this to work. So I guess just make sure that what you're doing is a legal move, but beyond that, there's definitely like a choose your own adventure element to this, with what variable you get rid of first, and then you sort of follow that path. But I did it with z, so I guess that's what I'm going to do here. So for my first pair, I just used the first 2. So I used 3x plus y minus 3z equals 31, and I used 3x plus 3y minus z equals 9. And I decided to get rid of z. So I said, okay, well, this is easier if I don't have to adjust both equations, if I only have to adjust one of them. Well, if I'm going to do that, then I got to get a plus 3z down here. So I have to multiply both sides of the second equation by -3. Right? -3 times -z will give me a positive 3z. So I'm going to leave the top one alone. So the 3x plus y minus 3z equals 31. Then I'm going to multiply both sides of the bottom by -3. So -3 times 3x plus 3y minus z equals -3 times 9. And so then again, leaving the top one alone, 3x plus y minus 3z equals 31. And then on the bottom, minus 9y minus 9z plus 3z equals minus 27. And let's see, then if I add down, oh, no wonder this looked weird. That should be an x, and that should be a y. I don't know what I was thinking about. So minus 6x minus 8y, no z term because we got additive inverses, and then this equals 4. Okay, if nothing else, I would look at this and say 6, 8, and 4 are all even. So you could rewrite this as -3x minus 4y equals 2. Or if you would prefer it written as 3x plus 4y equals -2, like if you multiply both sides by -1, that will also work. But I'm going to leave it like that for now and just move on to the second pair. So for the second pair, the one that I haven't used yet is the bottom of the original 3, the x plus 5y minus 6z equals 17. So I got to make sure I use it. So x plus 5y minus 6z equals 17. And then I just need any of the other ones. I guess I'm going to use the top, because then 3 is closer to 6. I only have to double this. I don't have to multiply by 6. So that should keep the numbers under control a little. So I guess that's really all I'm thinking about here. So 3x plus y minus 3z equals 31. So again, I'm going to try to do this where I only have to adjust one of the equations. So I'm going to multiply both sides of the bottom by -2. Because -2 times -3z will give me a positive 6z. And then we'll get the additive inverses, and we'll get rid of z again like we're supposed to. So x plus 5y minus 6z equals 17. And then we're going to multiply both sides of the bottom by -2. So -2 times 3x plus y minus 3z equals -2 times 31. All right, so we've got, I guess I should kind of section this off here because these are going to end up kind of close together on the page. So x plus 5y minus 6z equals 17. And then for the one underneath, I guess that'll be minus 6x minus 2y plus 6z equals negative 62. All right, so if I add those two together, we're going to get minus 5x plus 3y, no z term, equals negative 45. That's what 17 minus 62 is. Okay, so now if you look at what we got the negative 3x minus 4y equals 2, and then we've got negative 5x plus 3y equals negative 45. So section that off, and then for two equations and two variables, right? Because now we've got two equations that are just in terms of x and y. So we've got negative 3x minus 4y equals 2, and we've got 5x plus, or negative 5x plus 3y equals negative 45. All right. What I would probably do is I would probably try to get rid of y if we were going to do this by elimination, which I think we kind of should here. Otherwise, we're going to get a bunch of fractions. So I would try to get rid of y just because these y terms have opposite signs. So I would just think, all right, 3 and 4, the least common multiple is 12. So I'm going to aim for a negative 12y on top and a positive 12y on the bottom. All right, so multiplying both sides of the top by 3, both sides of the bottom by 4. So 3 times negative 3x minus 4y equals 3 times 2. And then on the bottom, we're going to have 4 times negative 5x plus 3y equals 4 times negative 45. All right, so then on top, we're going to have negative 9x minus 12y equals 6. And then on the bottom, that's going to be minus 20x plus 12y equals, let's see, it's going to be 90 times 2, so it's minus 180. And if I add those together, I'm going to get negative 29x equals negative 174. X is 6. 29 times 6 will give you 174. All right, so there's one number of the ordered triple, but now we need the other ones. So then we have these equations in x and y. We could use them to get y, and that's what you would do. So then the next thing would be to solve for y. And if we do that, so I guess I'll just use the first one. So minus 3x minus 4y equals 2. And we said x is 6. So minus 3 times 6 minus 4y equals 2. Or negative 18 minus 4y equals 2. And if you solve that, it looks like you get negative 5. Because you'll end up with negative 4y equals 20. And then if you divide both sides by negative 4, yeah, y is going to be negative 5. Okay, and now that you have those, then you can go back and solve for z. But when you solve for z, you have to use one of the original equations, because you have to use one that actually has a z in it. Otherwise, it's kind of hard to solve for z, right? So I guess, what did I use before? I think I just used the one in the middle. Oh yeah, because it doesn't have its coefficient's negative 1. That makes sense. 3x plus 3y minus z equals 9. All right, so 3x plus 3y minus z equals 9. And we know what x and y are. So this will be 3 times 6 plus 3 times negative 5 minus z equals 9. That's 18 plus negative 15 minus z equals 9. So that's 3 minus z equals 9, or negative z equals 6. So it looks like that means that if you multiply both sides by a negative 1, z is negative 6. And so then what we end up with as our solution, if you want to write it as an ordered triple, it would be 6, negative 5, negative 6. There. And that's what these are like. So all the steps that we kind of went through here, so going back up toward the top, you get one pair, like you take one pair of equations out of these original three, get rid of one of the variables, right? Figure out a way where you can eliminate one. Then you take a second pair of equations and eliminate the same variable. You're left with two equations with two variables, or two equations with two unknowns. That we know how to solve because that's section 3.1, right? We can just do that by elimination as well. And that's what I did to get that x is 6 and that y is -5. And then from there, once you know what x and y are, you can take one of the original equations, substitute in and solve for z, and then you've got it. So this does tend to get a little bit long-winded, but not number 3. And the reason that number 3 is not going to be quite as long-winded is because, look at these equations, they don't have 3 variables in them. Like, there are 3 variables there all together, right? Like, you can see x and y and z all in there. But the individual equations themselves, you're only getting 2 at a time. That actually makes things a little bit easier. So I would rewrite this a little just to kind of align everything. So all I'm going to do is I'm going to write this as though every term was there. Like, so I have a big gap here for the z, because I'm trying to line everything up to see what I should be doing next. Then we'll have 2y plus z equals 1. And then we're going to have 5x minus 4z equals 8. Because now I can see a little bit easier, you know, are there going to be variables that are easy to get rid of? Yep, because there's an additive inverse, right? You got minus 2y plus 2y. That would be my my pair. So I guess this is really my first pair, but it's also going to be my only pair, because once I eliminate y, then that third equation doesn't have a y in it. So I can just use that as the other equation of the 2 with the 2 unknowns. But my first pair is going to be the top 2. So 3x minus 2y equals 14. And then 2y plus z equals 1. And I'm going to add those together. And we're going to get 3x plus z equals 15. But right here, you can go to 2 equations with 2 unknowns, because you've got this and you've got this. Right? Like, this one's already set up with no y in it. So you might as well just use them. And I guess that's right where we're going, right? So 2 equations with 2 unknowns. So if we I'm getting way ahead of myself. So we've got 5x. I guess we just rewrite our equations. 5x minus 4z equals 8. And then 3x plus z equals 15. Then if we're going to solve that, I think it's going to be easier to eliminate z, because then we only have to adjust the second equation. If we try to eliminate x, we got to adjust both. So we're going to have 5x minus 4z equals 8. And then I'm going to multiply both sides of the one on the bottom by 4, so I can get the 4z. So 4 times 3x plus z equals 4 times 15. So then we're going to end up with 5x minus 4z equals 8, and 12x plus 4z equals 60. And if you add those together, you get that 17x equals 68. And if that's the case, then x would have to be 4. All right, well, if x is 4, we should be able to solve for z without too much trouble. So I'm going to use this bottom one, the 3x plus z equals 15. Since z has a coefficient of 1, that feels like it'll be faster, even if it's only slightly faster. So if we solve for z, so we got 3x plus z equals 15. And then if x is 4, we'll have 3 times 4 plus z. Whoa. All of a sudden, I can't draw. There we go. All right, so that's a 12. Looks like z is 3. All right, so now we got that. And then we got to go back and solve for y. And you can just pick any equation with a y in it. So like if I go up here, first one's got a y in it, so is the second. The second one's got smaller numbers. Let's go with that. So 2y plus z equals 1. So if we have the 2y plus z equals 1, but we know that z is 3, then we got the 2y plus 3 equals 1, or 2y equals negative 2, which means that y is negative 1. Okay, that's the missing piece. So we got our solution. So to write the solution out as an ordered triple, it would be 4, negative 1, 3. And there we go. So those are the best. If it's 3 equations with 3 unknowns, if there are ones where variables are missing, which is basically what we had here, those are way, way better. Because that kind of tells you, in a way, what, like if you're not missing a variable in all 3 of them, like maybe just in one of them, then that kind of tells you what to do, which is nice. But here, when you're missing multiple variables, then the part where you need to get like the 2 different equations where you just have the 2 unknowns, really you just got to get one of them, right? So that cuts down a lot of work. And then even the solving, like with less variables there, you don't have as much to do. So yeah, these are better, right? They're faster. All right, the next one, let's see what happens here. So I guess, again, kind of eyeballing everything. I don't really see a natural way to start. I don't see like additive inverses in there or anything. I guess maybe use the first and third and multiply both sides of one of them by negative 1. That way we can get the x's to add out. That might be the way to go. So for the first pair, what I'm thinking about is if I took x minus 2y plus 3z equals 5, and then I took x minus 5y plus 8z equals 7. And let's say I'm going to multiply both sides of the bottom by negative 1. That way I'll get a negative x, so I'll have additive inverses. So I'm going to leave the top alone. And then on the bottom, I'm going to multiply both sides by negative 1. And let's see, top staying the same, so x minus 2y plus 3z equals 5. And then bottom would be negative x plus 5y minus 8z equals negative 7. All right, and if I add those together, it's going to be 3y minus 5z equals negative 2. All right, so that's my first pair. My second pair, when I did it earlier, I just did the second and third and then multiply both sides of what would be the third one up there by negative 2. And then that way I could get rid of the x terms. So for the second pair, I thought, because you got to use that one in the middle, right? We haven't used that one yet. The 2x minus y plus z equals 8. Haven't used that one, so we got to use it here. And then I use the one underneath, the x minus 5y plus 8z equals 7. And then I thought, oh, if we multiply both sides of the bottom by negative 2, then we'll have a 2x and a negative 2x. Those are going to be additive inverses, so that seems like a good way to do it. So top staying the same, 2x minus y plus z equals 8. And then on the bottom, I'm going to multiply both sides by negative 2. So negative 2 times x minus 5y plus 8z equals negative 2 times 7. All right, and so then we're going to have 2x minus y plus z equals 8, and then minus 2x plus 10y minus 16z equals negative 14. If I add these together, that's 9y minus 15z equals negative 6. Okay. If there's anything noticeable right now, it's that 9, 15, and 6 have a common factor. They're all divisible by 3. So we could rewrite this as 3y minus 5z equals negative 2. Oh, look. We already got that. So what does that mean? Well, let's say if we didn't do this. Like, what if we didn't rewrite it? Because then maybe this will be like the more common thing, because this is working out to be pretty clean here. But if we have 2 equations and 2 unknowns, so I'm going to say, like, from that first pair that we got the 3y minus 5z equals negative 2. And let's say from the second pair we didn't notice that you could divide both sides by 3. Then you'd have 9y minus 15z equals negative 6. Okay, well, at this point, if you didn't see that the second one is a multiple of the first, then if you tried to eliminate a variable, you're going to get 0 equals 0, because everything's going to be eliminated. You're going to get additive inverses anywhere. So what you really want to do is, I think you'd be better off picking the one with the smaller coefficients. So you can't really solve this. All you can say is, well, we know that 3y minus 5z is negative 2. Okay. And typically what you would do next is you would solve for one of the variables. So I'm going to solve for y. So then if I add 5z to both sides, then 3y would be 5z minus 2. And then that would mean, if you divided both sides by 3, that y would be 5/3 z minus 2/3. Okay? So that's what y is. So this is one of those ones where you get infinitely many solutions. Like, that's what this is. And then you could solve for x, also in terms of z. So if we're going to solve for x, you would take one of the original equations, so something with an x in it. I just took the first one. So the x minus 2y plus 3z equals 5. And then I just have a thing that I got to sub in for y. So I'll have x minus 2 times 5/3 z minus 2/3 plus 3z equals 5. I guess you could clear the fractions here, or you could just deal with them. We'll do this one where we just deal with it. That'll be a little bit different. So then if I distribute the 2, I'll have x minus 10/3 z minus 4/3 plus 3z equals 5. And then if you distribute the negative, x minus 10/3 z plus 4/3, right? It's minus a negative 4/3, plus 3z equals 5. All right, well, we've got a minus 10/3 and a plus 9/3, right? I guess we could do something with that. And we're going to need to combine the constants in a second. So I guess the x I can leave alone, but everything else, I'm just going to write it with the denominator 3. So 10/3 and the 4/3, those are fine. 3z I could write as 9/3 z, right? Multiplying by 3 over 3. And then 5 is 15/3. So minus 10/3 plus 9/3 is minus 1/3. So I have x minus 1/3 z plus 4/3 equals 15/3. But I'm trying to solve for x, so I should put everything else on the other side. So, all right, well then you'd have x equals, so I'm going to add 1/3 z and then subtract 4/3. So I'm going to have 1/3 z plus 15/3 minus 4/3, or that x is 1/3 z plus 11/3. And that is the answer. So, okay, well then what does the solution look like? You can't write this as an ordered triple. No, you can't, because we don't have numbers. Gotta write it in set notation. So, what the solution would look like, it would be the set of all ordered triples x, y, z, such that x is 1/3 z plus 11/3. Y is 5/3 z minus 2/3, and z is a real number. That's what the solution actually would look like. And it was so long that I couldn't write the brackets just going left to right. I had to go to a second line of text. But that's what you get with the ones with infinitely many solutions. So really what this is this is a line in 3 dimensions. So it's like that picture on the front page where we're getting the intersection, but it's not a single point. It's an entire line. And that's kind of what it would look like. You would have one independent variable, and then you have 2 that are dependent on that one. So in this case, z is independent and x and y are dependent. All right, well then you kind of know what's coming here, I would imagine. If we had one where we had the infinitely many solutions, you know what hasn't happened yet? One where we get none. So yeah, that's kind of what that's where we're headed. But looking at this, I would start with the first 2. Because the y terms, there's a negative y and a positive y. The additive inverses are already set up. So for the first pair, I would just pick the first 2. So x minus y minus 2z equals 2. And then x plus y plus z equals 7. Because then if you add those together, you're going to get 2x minus z equals 9. And then for the second pair, well, let's see. I haven't used the third one yet, so I got to use it. So 3x minus 3y minus 6z equals 4. And I'm going to use the second one because the y term is positive there. And so the x plus y plus z equals 7. Because then with the one that's now written underneath, if I multiply both sides of that by 3, I'll get the additive inverses with the y terms, and we'll have something in terms of x and z. All right, so what we're going to do then is we're going to say the top one stays the same, and the bottom one has both sides multiplied by 3. So 3 times x plus y plus z equals 3 times 7. And then we're going to have, all right, we got 3x minus 3y minus 6z equals 4, and then underneath 3x plus 3y plus 3z equals 21. And if I add those, that's going to be 6x minus 3z equals 25. Okay, so we've got our 2 equations with 2 unknowns. So 2 equations, 2 unknowns. All right, so we've got x and z, right? So 2x minus z equals 9, and we've got 6x minus 3z equals 25. You might be able to see it here because the left sides are multiples, right? Like the bottom, this is 3 times what's up here, but that's not quite what's going on here, right? This is a 25, not a 27. So if you tried to eliminate a variable, I guess either way, if you tried to get rid of x or tried to get rid of z, you're going to multiply the top equation, both sides of it, by -3, right? So let's do it. -3 times 2x minus z equals -3 times 9, and then the bottom one staying the same. So 6x minus 3z equals 25, and then if I simplify the top, that's minus 6x plus 3z equals -27, and the other one's staying the same, 6x minus 3z equals 25, and we're going to get 0 on the left. Additive inverses with the x terms and with the z terms, On the right, we're going to get -2. Well, that doesn't work, right? Those aren't equal, so there's nothing here. So that means that there is no solution. Or, I think the way the homework wants it, the solution is the empty set. So the solution equals either the bracket empty set or the circle with a line through it empty set. Right, so this is where you know you've got something that doesn't work, where there's no solution. If you're trying to solve it and you end up with a step where you've got two numbers equal to each other that clearly are not the same number, that's the dead giveaway that it doesn't work. Although with this one, I think you could see it back here, because you could go, wait a minute, if the left sides are multiples of each other but the right sides aren't, this isn't solvable. Right, like that would also have to be true. And that bears itself out if you try to solve it. So if you do see it back here, that's great. I think then you could just stop there and go, wait, this doesn't work. And I guess it just kind of depends on how often you've seen these things before, right? I mean, if this is something that, that you've seen recently, then it's easier to pick up on back here. But if not, if you don't see it right away, that's fine, because if you go through and do the solving, you're going to run into something that doesn't make any sense, right? When you get that statement like that 0 equals -2, that's where you go, all right, that doesn't make any sense at all, so this just doesn't work. And there's no solution. Okay, next. There are some word problems in this section, so I stuck a couple in here at the end. First one, where Tasty Bakery sells 3 kinds of muffins: chocolate chip for $1, oatmeal for $1.25, and cranberry for $1.50. It says Charles buys some of each kind, chooses 3 times as many cranberry as chocolate chip, and if he spends $17.25 on 13 muffins, how many oatmeal muffins did he buy? Right, clearly he bought some because the total price ends in a 25. Right, couldn't get that just from chocolate chip and cranberry. So let's see. I guess we're going to need some variables. So let's say if we let x equal the number of chocolate chip muffins, and then I'm going to say let y equal the number of oatmeal muffins, and then I'm going to say let z equal the number of cranberry muffins. All right, so now that we know what's what, now we can start translating the sentences into equations. All right, the two really big things are in the last sentence. We know we spent $17.25. We know we bought 13 muffins. Those are actually 2 separate statements that are kind of compressed into one sentence. So we know he bought 13 muffins. And if X, Y, and Z are the individual amounts of the different types of muffins, then that would mean that X plus Y plus Z has to be 13, right? The number of chocolate chip muffins plus the number of oatmeal plus the number of cranberry, it's got to equal the total if those are your only 3 options, right? So that's true. And then let's see, that he spent $17.25. What that means is that it would be 1 times the number of chocolate chips, so 1 times X, plus 125 times the number of oatmeal, plus 150 times the number of cranberry, has to equal 17.25. So we've got 2 equations, and we need the third. The third is actually in the previous sentence, where it says he has 3 times as many cranberry muffins as chocolate chip. So 3 times as many cranberry as chocolate chip. So what does that mean? That means that if you took the chocolate chip, the X, and multiplied by 3, that would give you Z, the cranberry. So that means 3X equals Z. But to get this to look more like these other equations, I want the variables on the same side. So I'm going to subtract z from both sides and say 3x minus z equals 0. Okay. Well, now we have our system of equations. Because we've got x plus y plus z equals 13. And we've got x plus 1.25. Can't draw again all of a sudden. 1.25y plus 1.5 z equals 1725. And then the other one is that 3x minus z equals 0. Okay. And now it's three equations with three unknowns. So we go back to what we were doing. The first pair that I would pick would be the first and third, because you got the plus z and the minus z. So for the first pair, what I would do is I would have x plus y plus z equals 13, and then 3x minus z equals 0. And if you add those together, you're going to get that 4x plus y equals 13. Okay, so it looks like that's going to end up being helpful. Then the other, I guess the other situation that you could use here, I may have actually, I'm setting this up to go the long way, actually. I shouldn't be doing it like that. What I should be using is, because I jumped right on the additive inverses, the better thing to do here, actually, because I can see that I'm going to end up doing it longer than I have to, the better idea would actually just be to use the first two and eliminate y. Because then this one's already just in terms of x and z. Yeah. So you could do it the way I'm doing it, but you're going to stretch it out. So don't do that. Right? It's long enough already. Don't stretch it out any further. So I'm just going to get rid of this. I'm not going to do it that way. I'm going to get rid of y in the first two, which would mean that it would be helpful if I cleared those decimals in the second one. You could multiply both sides by 100 just to move the decimal point over, but if you look at what these are after the decimal point, you got 0.5s and 0.25s. 0.25 is a 1/4, right? Multiply both sides by 4 instead of 100. That'll actually clear those decimals. So that's what I'm going to do with this. So my pair, I guess now, it'll say first pair, but it's really going to be my only pair. It's going to be the top two. So x plus y plus z equals 13, and x plus 1.25y plus 1.5z equals 17.25. Then I'm going to multiply both sides of what's now the second one by 4. So the x plus y plus z equals 13. That's going to stay there. And then 4 times x. And actually, I gotta flip the sign anyway, so maybe I should be doing -4, but I'll do these things one at a time here. And right side will be 4 times 17.25. All right. So then we're going to have same thing on top, x plus y plus z equals 13. And then on the bottom, 4x plus 5y plus 6z equals, let's see, 4 times 17 is 68. 4 times 0.25 is 1. So that's 69. And then we're going to need to get rid of y, right? So then that way we can use the 3x minus z equals 0. So I'm going to multiply both sides of the one on top by -5. Because then I'll have a -5y and a 5y, and then those are going to add out. So -5 times x plus y plus z equals -5 times 13, and then 4x plus 5y plus 6z equals 69. Okay. Then, let's see, negative 5x minus 5y minus 5z equals negative 65. And then 4x plus 5y plus 6z equals 69. If I add those, that's going to be negative x plus z equals 4. Okay, now we're there where we've got the two equations with the two unknowns. All right, so the two equations with two unknowns. All right, so first one, I guess we're taking out of the original 3 where we've got the 3x minus z equals 0. The other one is negative x plus z equals 4. Oh, this is nice. We've got additive inverses already. Right, add them together, you get the 2x equals 4, so x equals 2. Right, so there's part of the answer. We're supposed to get the amount of oatmeal, so we're actually going to have to then get z, and then oatmeal is y, but it won't be that hard to get. So then if we're going to solve for z, all right, so negative x plus z equals 4, but x is 2, so negative 2 plus z equals 4. That means z is 6. Okay, that's cranberry. Right, because the 2 is the chocolate chip, the 6 is the cranberry, and then we're going to solve for y, which is the oatmeal. So one of the original equations was that x plus y plus z equals 13. And right, we got to use an equation with a y in it if we're going to solve for that, but this looked like the easiest option. So 2 plus y plus 6 equals 13. 2 and 6 is 8, so if y plus 8 is 13, then y must be 5. And that's the thing that we're supposed to get, right? That one right there, that is the oatmeal. All right, so 2 chocolate chip, 5 oatmeal, 6 cranberry, and I did check this actually, and it works. I clearly don't have room on this page to do the check, but it does actually work. Okay, one more, and it's another word problem. So Anna has 3 investments totaling $90,000. In 1 year, they earn interest at 4%, 6%, and 8% respectively. And it says that Anna's total income from investments is $5,800, and the income from the 8% investment exceeds the total of the other two by $600. And we want to figure out how much Anna has invested at 4%. All right, so this is going to be another 3 equations with 3 unknowns. The one thing that you got to worry about, maybe not worry about, but at least be aware of with the money type questions, there are going to be big numbers in this. You can kind of tell, right? There's a 90,000 in it already. That's a big number. And we're going to need some variables. So I'm just going to say let x be the amount invested at 4%, and then y will be the amount invested at 6%, and then z will be the amount invested at 8%. All right, and then let's see, first sentence. The 3 investments total $90,000. So these 3 individual amounts that are being invested, when you add them together, you have to get that. You have to get 90,000. So from the first sentence, we know that x plus y plus z has to be 90,000. All right. Then the third sentence with the total income from investments, we can get that too written in symbols. All right, so the investment income, like we can do this piece by piece. So if this first one's invested at 4%, the investment income for a year would be this. It would be 0.04 times x. The second one's invested at 6%. The interest income is going to be 0.06 times y. And the third one at 8%, 0.08 times z. So you add the three individual interest incomes together, you'd have to get the total, which is 5,800. Then the fourth sentence, that the income from the 8% investment exceeds the total income from the other two by 600. Okay, so the fourth sentence, there are a couple of different ways to write this. So it involves the income of the other two. I'm going to write those out first. So 0.04x plus 0.06y. And then the 0.08z exceeds this by 200. So if you took this, added 200 to it, you would have to get 0.08z. However, this is going to be a little bit easier to deal with if all the variables are on one side. The other thing that's probably worth it is clearing out those decimals. So that third sentence, I'm going to rewrite that. If you multiplied both sides by 100, you'd get 4x plus 6y plus 8z equals 580,000. Right, 5,800 but with two extra zeros. And then here, we could do the same thing, clear those decimals out. We'd get 4x plus 6y plus, I guess that would be 20, or, it's 600, not 200. I don't know where I got 200 from here. So that should be a plus 600. Sorry about that. And then something looked off. So yeah, plus 60,000 equals 8z. But usually you would write this with the z term over on the left and the number over there on the right. So I'm going to rewrite that one and just move both of those at the same time. So subtract 8z from both sides and subtract 60,000 from both sides. You'll get 4x plus 6y minus 8z equals negative 60,000. Okay. That's actually going to be pretty useful. So what we've got right now, right, so like there's one equation, there's the second, and then there's the third. So for my first pair, I'm actually going to use the two that we just cleared the decimals out of, because one of them's got an 8z and the other one's got a minus 8z. So we can just add and get rid of the z term. So in that first pair, we've got 4x plus 6y plus 8z equals 580,000. And then we've got 4x plus 6y minus 8z equals negative 60,000. And you could, before you add these together, if you wanted to reduce these, because in every single case, like these are full of even numbers, right? Like you could rewrite the bottom one as 2x plus 3y minus 4z equals negative 30,000 if you wanted. But I'm just going to add them together and then worry about that. So we're going to have 8x plus 12y equals 520,000. And then you could divide both sides by 4, actually. And you could say, well, then this is 2x plus 3y equals 130,000. If you divide both sides by 4, you'll get there. That's probably a little better. Then the second pair, we didn't use that first equation from the first sentence, so we got to use it now. So x plus y plus z equals 90,000. And then I guess I'll use the bottom one, since the z term has the opposite sign and we got to get rid of z here. So 4x plus 6y minus 8z equals negative 60,000. And I need to get an 8z on top, so I got to multiply both sides by 8. So I'm going to have 8 times x plus y plus z equals 8 times 90,000. And then I guess I'm just going to have 4x plus 6y minus 8z equals negative 60,000. And then if I distribute that 8, then I'll have 8x plus 8y plus 8z equals 720,000. And then I'm going to have 4x plus 6y minus 8z equals negative 60,000. And if I add those together, those z terms are going to add out. So we're going to have 12x plus 14y equals 660,000, looks like. Okay, well, all those are even. So you could rewrite this as 6x plus 7y equals 330,000. Divide both sides by 2 just to make the numbers a little bit smaller. All right, then down here, so we're going to have two equations and two unknowns. All right, so we're going to have 2x plus 3y equals 130,000, and we're going to have 6x plus 7y equals 330,000. It's probably easier to get rid of x since you wouldn't have to adjust the bottom equation to do it. So that's what I'm going to do. Multiply both sides by negative 3, so I get a negative 6x on top. So negative 3 times 2x plus 3y equals negative 3 times 130,000. And then 6x plus 7y equals 330,000. All right, let's see. That'll be negative 6x minus 9y equals negative 390,000. And then 6x plus 7y equals positive 330,000. And if I add those together, negative 2y equals negative 60,000, which then means that y is 30,000. So if we were getting the ordered triple, that would be part of the answer. But the only thing we actually have to do is solve for x, because we just need the amount that's invested at 4%. But we've got equations that are just in terms of x and y, so we can solve for x without too much trouble. And if we do that, I guess I'll just use the top one. The numbers are smaller. So 2x plus 3y equals 130,000. And then subbing in for y, 2x plus 3 times 30,000 equals 130,000. So then 2x plus 90,000 equals 130,000. And if you subtract 90,000 from both sides, you're going to get that 2x is 40,000. And so then that would mean that x is 20,000. And that is the answer. I guess with a dollar sign, right? Okay. So that would be the answer. And then I guess even though it's not solved for, z would have to be 40,000, right? Because 20 plus 30 plus 40 will give you 90. Sorry this is so long, but I wanted to get those word problems in there. And the individual problems in this section are so long that it's hard to not have this video be so long too. But I think that just about covers everything that would show up in this section. And if this one makes sense, then 3-1 is going to be easy, right? Because you've got to do all the 3-1 stuff in this, and it's less stuff generally. So I think that's true. If you can do 3-3, you can definitely do 3-1. So that's a big plus, right? That if you can do this section, then one of the ones before it is going to feel a lot easier.